let me give you a little background information. I started playing with antennas when I was working with crystal sets, and that was a while back. And after playing with crystal sets for a while, I finally graduated into a little bit more into the vacuum bulb stuff, and finally got my ticket, and I'm celebrating my 60th year with the same ham call sign. So I've been around a while, but I've always had an interest in antennas. But it's one of those unfortunate things that when I went to college, they wouldn't let me study antennas till I got a master's degree, and I didn't have time to do that. Actually, I didn't have the money is what it amounted to. So I never really got to study antenna theory per se, so I had to learn what I learned on my own. That was rather fortuitous, I think, because a lot of the things that are in the books are kind of gloss over the basic concepts. They just don't tell you what's really going on. And so I want to take a few minutes to really try and explain what an antenna is. Actually, it's so simple, and I think that's why they never get around to it. But on the other hand, I found out that the real antenna gurus don't even look at simple things. They are so involved in their real kooky mathematics and all that good stuff that they just don't truly understand what an antenna is, and therefore they just keep banging away at the same old thing. Now, the antennas that 99% of the people use today, a few more than that probably, are the basic wire antennas that Mr. Hertz developed in the late 1880s. Actually, before that a little bit, but somewhere back in there. And then James Clerk Maxwell did a bunch of theoretical stuff around 1880 something or another, and set the basis for the theoretical work. Well, all these fellows that go to study antennas in college, then that's their Bible. Well, unfortunately, I don't totally understand some of the mathematics involved in that, curls and divs and all those kinds of things. And so I have to look at things from a simple viewpoint. So I thought you fellows might appreciate a simplistic view of what antennas really are. And with that background, then you can go ahead and you understand all the antennas. But I really apologize for not having a blackboard or something, but it's one of those things that happened that couldn't work. Let me explain what an antenna is. In its simplest form, it is a capacitor in series with a resistor. Now, the resistor is actually what we call the radiation resistance. Now, an antenna has a resistance, and depending on its configuration, that resistance will vary. The theory says, okay, you put a dipole in free space, got 73 ohms resistance. If you put a vertical up, it's half of that. I mean, those are some rules of thumbs, and those don't even hold very close either, because there are a lot of variations of that theme. Now, the capacitor is actually the capacity between the two elements of the antenna. In the case of a dipole, it's the capacity between the two elements. In the case of a vertical, it's the capacity to ground, or theoretically it's the capacity to the radials. But the radials are the other half of the antenna. Now, when you look at the antenna, in order to be able to pass current through that radiation resistance, you have to have a resonant antenna. A couple of ways to get that. One is that you build the antenna basically a quarter of a wavelength long if it's a vertical or, a half-wave dipole. And that means the inductance and the capacitance are equal, and therefore they cancel out, and therefore you can put maximum current through that radiation resistance. Well, that's the simple theory. Now, let me just allude to that a little bit more, and that is that when you have an antenna, as you pass current through that antenna, the current will develop a magnetic field. Now, the magnetic field, as it changes, in other words, as it increases or collapses, it will create an electric field. This is the basic concept of a generator, alternator, whatever you want to call it. So you pass current, you make a magnetic field, and that in turn creates an electric field. Now, unfortunately, those two fields are really 90 degrees out of phase because one created the other. Now, I might also comment that an electric field, as it collapses, or increases will generate a magnetic field on that same piece of wire. So this thing just goes back and forth. One of the unfortunate things about an antenna is that you have a very large electric field surrounding it because the electric field and the magnetic field are 9 degrees out of phase. In order for the thing to radiate, they have to be in phase. In other words, they have to occur at the same time. Now, basically what happens is that as the electric field propagates, it propagates slower than the magnetic field. And when you get out to roughly a third of a wavelength from the antenna, they caught up with each other and they're basically now in time phase and they start radiating. Now, you can get deeper into it and say, well, okay, now the electric field and the magnetic field are always going to be orthogonal to each other. And that is that one of them will be, if you will, vertical, the other will be horizontal. And now this gets you into, okay, what kind of an antenna do you really want and what kind of purpose do you want to use it for? Well, we all know that a good vertical antenna has a low angle of radiation along the ground, and that's a good thing for some applications. On the other hand, a dipole, if you stop and look at that, the current's going along the wire, and it creates the field such that it's up. So a horizontal antenna makes horizontal polarization, we call it, and the radiation then is perpendicular to the antenna, and therefore your horizontal antenna radiates straight up. Now, depending on the height of the antenna, in the case of a dipole, you wind up with what we call a pattern that's a function of the ground. In other words, if you put it at a quarter of a wavelength above ground, there's two signals coming out of the antenna. Just a signal, but it surrounds the antenna. Okay, but think of it as two signals. One of them going straight up, the other one going straight down. Well, the one going down is going to hit the ground, and it'll turn around and reflect off of it and go back. But now, if it's a quarter wave above ground, then that quarter wave goes down, turns around, comes back 180 degrees for that traverse in there. The quarter wave is 90 degrees, so half wave would be 180. Now, you get into problems where the radiation patterns can cancel depending on where the antenna is located. So generally we like to have a dipole for maximum high angle radiation to be a quarter wave above ground. If you put it at a half wave above ground, it turns out that you get almost complete cancellation, and therefore there's no high angle radiation, but rather your maximum signal now is at lower angles. But now you got another problem. The problem is that a signal that propagates along the ground will actually be absorbed if it's a horizontal polarized signal. In other words, a dipole allows the antenna to go along the ground. On the other hand, if you turn the antenna vertical, and if you build either a vertical or a vertical dipole, it is not absorbed by the ground in the same way, and therefore you get good low angle radiation out of it. So that's why you use a vertical antenna for AM broadcast. Now, if you want to get on 80 meters or something, you're really not going to be talking to anybody locally, so to speak, on ground wave. What you want to do is go ahead and propagate a high angle and let it come back down, and you will get good communications around the area. Now, by the same token, if you want to talk more than about round number, 750 miles, then you really ought to be using a vertical antenna to get a low angle radiation out there at that distance. And that's about where the two cross over, where you have the signal from the vertical or the horizontal antenna will cross at roughly 750 miles. So for the longer haul stuff, you need a vertical. For the short haul, you need a horizontal. That says, well, now, let's think about that for a minute. Let's talk about 20 meters, or 10 meters, or 15, or whatever. So all of us put up a great big old beam antenna, a great big horizontal beam, and we wonder why we can't talk to somebody. Well, the problem is it's a horizontal antenna. The horizontal antenna tends to have a higher angle of radiation. If you get that horizontal antenna high enough, it will begin to give you a pretty good low angle radiation. But if you really want to work some DX, take that horizontal and flip it vertical, get that low angle radiation, and go out there and chase that DX with it. Now, on the other hand, you say, well, that seems to be a bit of a problem, and the problem is that it's a mechanical problem. You have the antenna. How do you turn it up and work it with the tower? Well, the tower is going to cause you some mistuning problems. So what you have to do is retune it for that. But if you'll do that, and as a matter of fact, if you look around, I don't see it much anymore, but back in the heydays of CB, what'd they do? They had vertical antennas, right? But there again, the CB was predominantly local stuff. So they really got good propagation along the ground. And then they found out, hey man, we can work DX. So now the CBers get on and talk all over the world with these vertical antennas. So they figured that out a long time ago, but most of the hams never got around to thinking that way. So if you really want to get out there, go use a good vertical antenna. And if you want a whole lot of gain out of it, just go ahead and turn your beam up so that it's vertical, and then away you go. Well, that has some mechanical problems, but hey, you know, everything's got a problem somewhere, so you got to trade one of them for the other. The theory, though, that if you really look at and want to look at what propagation looks like, you have to consider your antenna being somewhere above ground, and it's going to have a signal that's direct, and you have another signal that reflects off of the ground. Now, those two, if they are additive, that's a good thing. If they subtract, that's a bad thing. Well, now, if it's a horizontal antenna, they tend to subtract, whereas if it's vertical, they tend to add. And this has to do with the dielectric constant of the ground and all that other fancy stuff. The point is, though, that, again, if you want low angle, use a vertical. You want high angle, you know, to talk 75 meters around the local area out to, you know, rag you out to a couple, 300 or 400 miles, use a good horizontal antenna. So that's the basis of deciding what type of a system you really want. Now, you can go on into to what you do and how you do it, and let me just talk a little bit about the antennas and antenna efficiency. Now, as a general rule, most of us like to have a good beam antenna. Well, that's fine. What's the optimal spacing on a beam? Well, if you look at the book, it'll tell you that the radiation resistance is a function of the spacing of the antenna. Now, if you come in less than 1/10 of a wavelength, then the radiation resistance of the antenna goes down very low. On the other hand, if you give it about 2/10 spacing, good reasonable radiation resistance. Now, what does all that mean? Okay, now let's assume for a moment that you have an antenna and it has the radiation resistance, but there are also loss components in the matching network and also in the dipole itself. You say, well, it's not very much, and it really isn't that much on a big dipole. But as you start squeezing the elements down, what happens is that the radiation resistance goes down, your loss resistance stays about constant, and therefore your efficiency starts falling off in a great big hurry. Now, let's take the same thing and let's talk about small antennas. Mobile mounts on 75 meters is a good example. Okay, now we have, because they're small, the radiation resistance is very low. Now, I can tell you that on a real good day, if you got a real good mobile rig and you really got everything grounded the way it ought to be, you can get about 3 ohms radiation resistance out of a typical 8-foot whip on 75 meters. Well, you say, well, hey, so what? Okay, let's just say that we got about 3 ohms out of that thing. Now, let's talk about the actual loss resistance in there. Well, you had this big loading coil, and there's a whole bunch of loss resistance in that coil. Now, I'm not talking about DC resistance. That's pretty trivial. What you have, though, is your current passes along a wire, then you have a loss of a resistance there. It's an RF resistance because the signal only travels on the wire itself, on the external part of it. So what happens is now you can develop a pretty high loss resistance. And typically, if you go out and measure it, you'll say, well, okay, it looks like about 15 ohms. Now, what's the efficiency of that antenna? Okay, the efficiency is actually the radiation resistance divided by the sum of the radiation plus loss resistance. Let's turn that around a little bit and let's say, okay, now what is the real efficiency? The amount of power you put in versus the power you get out. Okay, the power you put in is your total power, or that's going to be radiated. Oh, I'm sorry. The total power is the actual total resistance where you have the loss resistance and the RF resistance. The output power is actually the radiation resistance. So you simply take the radiation resistance divided by the sum of the radiation plus the loss resistance. Okay, so now we got 18 ohms total resistance, but we only got 3 ohms that we're radiating. So what's the efficiency of that? It's 3 divided by 18. Okay, that's about 12-15% efficiency. Now, what that says on 75 meters, if you have a real good mobile antenna, you put 100 watts in, you're radiating about 12-15 watts. The rest of it's just going up in smoke. Now, that applies to all your antennas. Let's take a good vertical. Okay, now the book says in order to get a really good vertical, you need to bury 120 radials. That's a requirement by the FCC for standard broadcast antennas. What they don't tell you is that you can get away with 4 radials if you will raise those radials above ground a little bit. Now, what that says is that in a standard vertical antenna with all these ground radials, all you're doing is heating the earthworms because you have a lot of loss resistance through that ground trying to get to those radials. So now you've added resistance in there as loss resistance, and so your efficiency of that antenna is just going to go way down. Now, I can tell you that I can show you that any AM broadcast antenna is blowing about half its power eating up the ground around there. Now, you'd say, well, gee, that's a lot of power. Station runs 10 kW, well, 5 kW is going into heat. The rest of it's going to be radiated. Now, by the way, the optimum angle of radiation out of a standard vertical is at about 22, 23 degrees, somewhere in there. So that's why, you get pretty good signal close in, but as you get further out, that signal is going over your head. But that's also the cause of what we call the nighttime problem in AM broadcast, where you have the signal, part of it's radiating up, part of it's going along, taking off the way it does. And when the vertical signal comes around and comes back down from the ionosphere, it turns out they're about equal at some point out there, and you get cancellations. And that's why the FCC says, okay, you got to shut this sucker down at night when the sun goes down, because that's when the ionization gets better and it starts propagating vertical. So you have to close the thing down as the sun comes down, unless you have a clear channel station, because you can bounce off. Maybe you don't hear the radio station 20 miles away because of that signal, but you might hear it 1,000 miles away, and it's going to clobber somebody else's signal. So they shut you down at dark unless you have a clear channel designator. Now, let's talk about propagation just for a minute. I'm just trying to cover the waterfront here. Let's talk about what does the ionosphere do for you? Well, as the signal goes up and hits the ionosphere, depending on how well it's ionized, in other words, from the sun coming down, the solar radiation, all that, you can have a loss in the ionosphere as low as about 3 dB. So it'll go up, turn around, and come on back down. Now, it turns out that as your distance goes out, you lower the angle for a longer distance, it starts coming back down. You get into other problems that cause more loss in there. But we'll come back to that in a minute. Now, as far as in a situation like we have today on HF, the bands are lousy. Now, what happens? Well, the ionosphere is not ionized the same way it is, when it's up on the top of the sunspot cycle. Right now, we're just rubbing along the bottom. Your typical ionized layer up there now has a reflection coefficient that's something like, zilch. There's just hardly anything comes back down. Now, once in a while, it'll open up just for a little while, maybe on 20 meters or something, but that's about it. So even on 75 meters at night, propagation lousy. During a good time, shoot, man, you can flick your wristwatch and somebody in California can hear it on 75 meters, but you can't do that right now simply because the ionosphere is just not working in conjunction with what we'd like for it to be. It'll turn around one of these days shortly. In fact, I think it's already turned the hill, and so all we got to do is wait another 5 or 6 years, and we'll have good propagation times again. Now, those things come in 11-year sunspot cycles, and I've had times when, for example, one time I had to make a trip from Dallas to St. Louis, and I had a KWM1. And unfortunately, it was a 12-volt system. The old car I had at the time was 6 volts, so I put a battery in a tub in the back seat, and I'd talk, and then at night I'd charge it up while I was in the motel. Next day I had a good full battery, and I'd talk all day long on that. But what happened was that I was running about 100 watts, but I started just as soon as I left Dallas. One of the guys I was talking to was out of somewhere in Alaska. I think he was at Fairbanks. And no, I'm sorry, he was up on the dew line somewhere, but somewhere up in Alaska. Anyway, he asked me where I was going. I said, well, I'm going to St. Louis. And he said, well, you know the best way to get there. And I said, no, I'm just going to take a map and head off that direction. He said, well, you go to so-and-so. When you get to that point, you call me back. So I called him every time I got to the next point. And he would say, well, now take such and such a road and do so-and-so. That worked all the way through that whole trip. Now, there was other things. I mean, it was incredible signals. And I wasn't really chasing DX. I've never really enjoyed that. But, I'd just get on the air and I'd say this is, W5QJR Mobile, and somebody'd come back and we'd chit-chat for a while. And he said, I'm in, Young Dung Po or someplace. And through that process, without chasing DX, I logged 54 foreign countries that weekend. But that's when the propagation is good. When it's not good, you can't talk across town hardly. So that's just Mother Nature, and you just got to live with it. So what do you do to really get the best out of it? Well, you got to pick the frequency you want to operate on. You can always depend on talking to the repeater up here to the tower on 2 meters, but you can't depend on anything at the lower frequencies. Now, I'm anxious to things to get a little bit better. I want to get on 160, but I can't do it down here. I just don't have the space for it. In fact, I'm just in a rent house right now. Let me add to the commercial just a little bit. The reason I'm down here, actually my home is in Georgia. I retired about 1996, and in 86 I bought a pecan orchard in Georgia. And I thought, okay, I'm going to sit there and lay under the trees and watch the pecans grow. Seemed like a good idea. So anyway, that's what I did. Well, being a typical ham and curious about things, and I sat down and said, well, now what really makes an antenna work? And so I went through the same concept I just explained to you fellows a while ago, just how simple the antenna is. But one of the problems I told you about was that the electric field and magnetic field are 9 degrees out of phase. Well, why don't we fix that problem, and then maybe some other good things will happen? So I said, okay, let's do that. So I came up with a concept of another antenna and was able to actually generate the 2 signals in time phase. Now that says, okay, the electric field and the magnetic field are very efficiently integrated right at the antenna. And because of that, now rather than having, 73 ohm, I'm getting 170 to 200 ohms radiation resistance. Now I do have a little tuning coil in there, and that, of course, got a little bit of loss in it, but it turns out that typically I'm running somewhere in the neighborhood of 99.6%, that sort of thing. Some of them, because I use a smaller antenna, might be down in the neighborhood of, 80% or something. But now, for example, on 40 meters, I use an antenna, and the element on the thing is a little over 1 inch in diameter, and the whole antenna is about that long. Now, how do you say, well, how do you make that thing do what it does? Well, it's just simply a case of a little bit of change in configuration. And what I'm basically doing, voltage feeding a short dipole. Now, when I do that, the actual voltage applied to the dipole in the center of it is such that you have a high voltage on the feed part of the element, if you will. At the other end of the element, there's no connection to it, so there's no voltage there. So the voltage you apply is across that short element, and that causes a high current to flow, and that current flows up through that element, creating a magnetic field. But since I applied a voltage to it, the voltage was already there, so the voltage and the current are actually in phase. And for that reason, I called it an EH antenna, just simply to say that it's in phase. Well, if I go back in history just a little bit, I told you that they developed the antenna concept, Hertz did, back in the 1880s. In the 1980s, there was a fellow in Scotland, college professor, and a ham, and Mr. Hatley says, what if? Now, this is one of the most brilliant what ifs I ever heard. He said, what if we take some electric field, some magnetic field, and we combine them? Can we get radiation out of it? Well, there's another fellow that was a professor up there that happened to be a physicist, and he looked at it and he said, why not? Well, about the same time, there was a fellow came along from Egypt and wanted to study under Dr. Hatley. So he has this idea, so I said, okay, now let's work on this thing. So the three of them kind of worked it together. And they finally built an antenna, and they developed a scheme whereby there was a horizontal plate, if you will. Now I'm going to just tell you about a vertical right now. A horizontal plate above ground plane. Now if you apply voltage to that, there's an electric field that develops between the two plates, obviously, but there's also a magnetic field that rotates around those plates. So now they had a way to make a magnetic field, so they put another element up on top of these floating up there and put a voltage on that, so that makes your electric field, so they combine the electric magnetic field in what they call the zone of conversion, and it caused radiation, and so they built a small antenna. It worked really well. There are several of these things around the world that are operating. They have some problems that they didn't realize at the time, and it kind of virtually ruined their business. But what happened was that they tried to sell AM broadcast antennas, and they created this thing, and it worked rather well. But in effect, their antenna is really not a true vertical in the sense that we think of a vertical. It's actually really more like a dipole. And so unless you get the dipole high above ground, you don't get any radiation out of it along the ground. In other words, the angle of radiation is proportional to the height, where you get a maximum from a dipole a quarter wave above ground. Now, if you ever built a true halfway vertical, just let the bottom end of it touch the ground, and you can actually feed it off the ground as a voltage-fed antenna. Now what you're doing, you're getting your current maximum right up in the middle at a quarter wave above ground, and you get a tremendously good antenna out of that. I have built them because back in Georgia, I had some great big tall pine trees next to the house, and slingshot and all that sort of stuff. I had a pretty good antenna hanging up there. But anyway, their antenna, even though it was small, wouldn't radiate well along the ground. They sold a bunch of them and collected a lot of money, and the customers weren't very happy because they ran off on them. Well, anyway, this was about 100 years after Hertz made his discovery about resonant antennas. So when I retired, I got to looking at things. I noticed what they did and began to see the flaw in it. So I said, okay, I'll find another way to do it. So I developed what I call the H antenna, and that way it's just a short dipole with a voltage feed in the middle of it, and that works rather well. Well, what I was telling you was the reason I'm down here is that I got patents on this, and there's a company here in town called Diversified Technology that wanted me to come down here and develop that antenna for the military. So that's what I'm doing here. When I get through, the government sponsored is to develop antenna to cover 1.6 to 1,000 megahertz. Well, I'm having some great luck with 1,000 megahertz antenna. They're about that big. The 1.6 megahertz and up, some of those are going to be I'll probably make it 3 or 4 inches in diameter. I haven't really worked on the lower one yet. Just finished one the other day that covers 115 to 150 megahertz. Now, one of the things about it, let me go back and talk about some theory again. I don't want to bore you guys with a lot of detail, and I wish I had a blackboard. But let me just say that there's a couple of terms that we use in antennas. One is the Q of the antenna. Now, normally you all think about Q in the sense of a quality factor. In this sense, Q has nothing to do with the quality. Q is simply a measure of another set of parameters. Now, in this case, Q is equal to the capacity of reactance divided by the resistance. Now, and it's also equal to the actual operating frequency divided by the bandwidth. So if we measure the bandwidth and we know some of the other parameters, like for example, the capacity of the antenna, then we can figure out what the radiation resistance is. And so you can manipulate that equation any way you want to look at it. Well, what it says, though, is that because I can develop high capacity and high radiation resistance, then I can get some really good wide bandwidth. So I've got a little antenna that's less than a half inch in diameter and about that long, and it works exceptionally well between 115 and 150 megahertz, which is one of the military bands that we work on. I've got another one, and I apologize for not bringing some of these in to show you, but I didn't find out till this morning I was going to give this lecture. So I didn't come in with blackboards and all the other good stuff, because nobody told me. I offered to do it, and they said, okay, great, we'll think about it. And so I came in this morning, they said, hey, you're on lecture series. Okay, fine. So I apologize for not having the blackboards and some demos to show you. But anyway, from a standpoint of technology, I can simply tell you that this is the latest technology, and it is a big benefit to the military. Now, I'll give you one example that's kind of interesting. There's a radio that the Marines use. One of the most popular ones covers 30 to 90 megahertz. Well, that's fine. Well, what kind of antenna they got on that sucker? It's an 8-foot whip, actually. But what do the Marines call an 8-foot whip out in the battlefield? A mortar magnet. And they don't like that. Because you can imagine that thing sticking up there and say, oh, here I am, shooting me, So we've come up with an antenna that's about that big to put on those same radios, and they're going to be tickled to death with that. And it's just, just simply a case of being a covert antenna in this thing. It wasn't designed that way. And as a matter of fact, it's kind of humorous that when I retired the first time, back in 96, I had this pecan orchard up in Georgia. And there were two reasons I bought it. One is that I had heard that I could make some money off pecans, and the other was that I had, 65 acres, and I could grow me some good 160-meter antennas out there. Well, then the good Lord came along and gave me this idea, and now I can put a 160-meter antenna about my height, set up on a little bit of tower up here, and just go banging away with it. So it's kind of funny that I don't need all that room for my antennas anymore. So I think the good Lord just played a joke on me there for a while. But anyway, I think I've said enough about antennas for right now. What I want to do is open this forum up, and I want to get your question. I'm trying to answer, what do you want to know about antennas? I think this is important, and that we get your comments. I try and satisfy your curiosity of what an antenna is and what it can do for you, rather than me just talking in the dark here. So let me just start around the room. Go ahead. What is your comment, sir?
Well, I was trying to figure out how to build a half-wave end-fed wire antenna. What sort of matching circuit can I use?
All right. Do you want a vertical or horizontal?
Well, my thought was to have like an L to try to get some elements of both.
Okay. When you have a half-wave antenna, you're actually, at the ends of the antenna, you have a very high impedance, high voltage, right? Now, if it's a short antenna like a quarter wave, then you're going to have a current feed. But here, a half wave, you're going to have a voltage feed. Now, most of your antenna tuners are set up to allow you to feed a voltage feed. Now, what you want to do in this case, use an L antenna, that's fine. What you want to do is to have a decent ground. Now, it only takes maybe, one or two radials, and they only got to be, what frequency do you want to get on it? 80, 160, or 80 meters? Okay. On 80 meters, if you put out a ground wire, just one wire, and run it out 20 feet or so, you're going to find out that it's going to work pretty well as a counterpoise. Now, if you put more down, it's even better. But what it amounts to now, because you have a very high impedance, you have very low current through that radial system, right? So what's happened now is that you're going to feed it with a high voltage feed because you have that high impedance. And if you look at any of your good antenna tuner schematic diagrams, it's just simply a coil, if you will, and a capacitor resonated at that frequency, and you tap the antenna down on the coil till you get the impedance that you're looking for. Now, typically the impedance of that thing is going to be maybe 1,000 ohms or maybe even higher. So you just tap it on that coil until you get maximum current flow in the antenna, and voila, you got it made. But actually what you do is look at, with a visual meter, preferably, or really preferably get a good impedance meter, but if you don't have that, use a visual meter and simply look at your antenna tuner input and say, okay, now here's, you tune that until you get a minimum visual. Then you're going to be in Fat City and it'll work great. Now, what's happened is if you take a half wave, remember now your current's going to be a quarter wave above ground. Okay, you're going to get good radiation along the ground, but you've got a horizontal component, you're also going to get pretty good high angle radiation. It's a great rag chew antenna. All right, let me go back to the back. Does that answer your question? I'm sorry?
I'm new enough. I'm just listening and taking notes.
All right, well, let me just go around the room here.
I'm kind of doing the same.
Okay.
I have trouble in the relationship between impedance, antenna impedance and radiation resistance. For instance, had a discussion at a breakfast, and I was talking about the big wheel antenna. Familiar with the big wheel?
I need to understand.
Dr. Mellon and W1IJD.
Well, explain it briefly so everybody understands what it is.
Okay, it's essentially three full wave loops in parallel. Three full, sort of like a clover leaf.
Okay.
Okay, but it's three full wave loops fed in parallel at the beginning. Good 2 meter mobile antenna. Okay? Well, the impedance is very, very low when it's parallel and you need a strap in order to bring the impedance up. Okay, so I'm thinking, well, let's raise the impedance of that. And I made the comment, and it'll be more efficient. And they said, no, raising the impedance doesn't raise the radiation efficiency. I said, I don't know enough about antennas to know whether they're right or not, and I'll just back off.
All right, well, let me try and answer the question this way. There's actually no direct relationship between the input impedance of an antenna and the radiation resistance. All right, now that's just a fact. Okay. Now let me try and...
I suspected they were right, so I didn't dare...
Well, let me try and give an example to understand exactly what I'm saying, okay? Let's say that you have a vertical antenna. It's just a grounded vertical, okay? You feed it at the base. Now, if the antenna is short relative to a wavelength, maybe it's a tenth of a wavelength or something like that, you're going to have very low radiation resistance. The input impedance of it is going to be two things. There's a resistive component and an inductive or a capacitive component, right? So you have to put a coil in there to make the thing resonant. Okay. Now then your impedance now is whatever the transfer is back from the radiation resistance plus the loss resistance. So now you have a complex quantity, okay, that you've got to satisfy. So now you have an impedance in here that's really not directly related to the radiation resistance because the impedance is going to be totally different.
Okay, let's stay away from the coil then, and let's go from full wave loops to feeding those three branches by folded dipoles. Okay, three folded dipoles, 300 ohms. It comes back to that center. They're in parallel, so it's 100 ohms.
Okay.
Okay. So I said, well, that should be more efficient because it's 100 ohm. It's three. It's 100 ohms instead of somewhere around 15 or 20 ohms.
Okay.
That should be much more efficient. So I said, no, there's no relationship between them.
Well,
now, dare to argue.
Well, now there's a slight relationship in the fact that if your feed point impedance is low, how are you going to make it match the transmitter that's 50 ohms?
What do they call it? Hairpin loop.
Okay, but you got to match the impedance with an antenna tuner, right?
No, hairpin loop that brings it up to 50 ohms.
Okay, if you can match it that way, okay. then your efficiency is going to be extremely high. But in generally speaking, when you have an antenna that has a low impedance, you need to use an antenna tuner to bring it up to 50 ohms, right? So whatever loss is in the antenna tuner has to contribute to the efficiency problem. Okay? Does that clarify anything?
Yeah, okay, so they were right, and I was right not to argue.
Okay. You, sir. Back in the back. Okay, go ahead.
I want to know how to make that short 160 meter antenna.
All right, let me explain it this way. In about, hopefully, another week or so, I'll have my website back up on the air, and it'll give you all the details of each antenna. Well, the website is www.eh-antenna.com. And like I say, I tore it down because I wanted to get rid of a bunch of old junk, and I'm trying to get it put back together and get it up again, and hopefully in another week it'll be up. It'll give you a lot of details about what the concept is, and then when I get time, I'm going to go in there and put some more details of what the antennas are. In other words, I'll design a 160 meter antenna and I'll put it in there. Okay. Right now, there's a couple of things you can experiment with on there just to see what the concept is. But I just haven't had time to get it all done. And I'm so busy out there trying to get these military antennas going. But again, some of those, particularly the 1.6 to 30, I think a lot of hams would be interested in that one to get that one done. But at the moment, like I say, go look at the website. Give me another week or so before I get it back up again. And you'll see what some of those are about. And then as I get time, I will add antennas to it. I just haven't had time to do it. You, sir.
I'm just sitting here listening, thinking that really nothing matters if I can't hear anything from the guy on the other end. And with me, anything that's vertically polarized, my noisy environment that I live in electrically causes me so much plague with noise that I can't hear a thing. It has to be horizontal for me to hear anything. And apparently my experience is not something that's peculiar to me. My neighbors that are several miles away that are hams tell me the same thing. When they go to vertical antennas, noise wipes them out.
Well, and the reason for that is that your noise is primarily an electrical noise as opposed to a radiated noise, right? Most of this is coming down the power lines, by the way.
Just crackling sound, yeah.
All right. Now, what happens is the electric field can propagate along the ground better than in a vertical mode rather than a horizontal mode, and that's why your horizontal antenna is so much quieter. Now, what you need to do is take a little handheld radio and walk down the power lines and figure out where the real problem is. What you got is some insulators that are arcing. Now, you don't see the arc, but that's what's going on. And you walk down the thing and find out there are these ground wires coming down the poles and find out which one you got the most goody on it.
Yeah, I live right on a high-tension transmission alley, goes right by the house. And so I'm plagued with it, but then my neighbors that I like to say are a couple of miles away, they're just as bad off as I am. They're hams.
Any ham that would move next to a high voltage power line is wrong.
Well, I've got a buddy pole. I don't know if you're familiar with buddy poles or not, but I like to operate portable sometimes. I take that buddy pole with me, and I've tried, it's set up for a guy who wants to be a tinkerer. So you can make it be a dipole, you can make it be a vertical. Right. And all the guys on the news group are always talking about how much better they do when they use the vertical orientation, rather than using the dipole orientation. So for me, it's just the other way around, because every time I turn it vertically, all I hear is noise.
How far apart are your buddies?
Oh, this is they're up, in other states. These guys are telling us how much.
What band are you on?
Huh?
What band?
20 meters probably.
20.
Yeah. But I took it to Tennessee, and I had the same thing. In Tennessee, I turned it up vertically, couldn't hear anything but noise. Turned it horizontally, I heard less noise, and I could hear the DX then.
Well, unfortunately, that's just the nature of the problem. But if you're along a high voltage power line, but still, what happens is that noise is actually energy that's being wasted by the power company. And they would like to know that you got that problem. They'll come out and fix it. But most of the guys that work there don't understand what it is. And so you got to say, okay, now the main problem is right here on this pole. And your insulators up there need to be washed off. And then generally what happens after a good heavy rain, they get a little quieter, right?
Sometimes, I've read it's a good idea to go out. One time I read guys should go out with a sledgehammer and beat on the pole. I read another guy said he done that one time with disastrous results. Don't do that.
Well, of course, there's the old saying, you could take a squirt bottle and squirt and wash the insulators off, right? But that's equivalent on the ignition coil, not a smart thing to do. You, sir.
I mainly run mobile, and as you pointed out, the big problem is ground resistance with a shortened antenna. I was thinking about trying to run a loop for 80 meters on it. Got any comments?
Yeah, lots of them. I got involved with loop antenna a long time ago. And I did a lot of research, and there wasn't anything available on it. So I wrote a book back in '84 on loop antennas, the only ones that have been written. In fact, in the AAA antenna handbook, I had an article in there, I think it was in chapter 5, and it was in there for years. I don't know if it still is or not. But it talked about the loop antenna. In a conventional loop antenna, until I came up with this new concept, I considered the conventional loop probably about the best antenna you can have. Now, I'm talking about what I call a small loop, where the total circumference is less than 1/10 of a wavelength. Now, if you build one of those and you just set it up vertically, set it on the ground, whatever, right? The thing that makes it work so well is that the actual radiation from that loop is perpendicular to the loop itself. In other words, on the vertical sides of it, you get vertical polarization as it comes around this way. Then you got horizontal polarization, right? Now, it's also what they call a magnetic antenna, and for that reason, it's a whole lot quieter than either the horizontal or the vertical. It's an excellent antenna. You might want to build one of those on 20. But you actually make the circumference less than 1/10 of a wavelength. Now, one of the problems you get into is that there's a very high voltage at the top of the loop. Now, I've seen some really snazzy high voltage capacitors out here. The great big glass bulbs out there, right? And that's what you really need on one of these things going to run any power. But they work very well. Well, now the problem is even 1/10 of a wavelength down on, 80 meters? Mobile? 1/10 of a wavelength, you're going to be 8 meters. Now, that would be the circumference of it, right? So that's about 24 feet. Well, that's a little bit bigger than you want to put it on the back of the truck, right? Okay, so you squeeze it on down, and what happens now is your radiation resistance comes lower and lower because it's a function of the diameter of the loop. All right, now, when that comes down, you also have a problem now with the bandwidth of the loop. It gets really, really narrow. So you got to be very critical how you tune the thing. All right, now, one of the phenomena of this concept that I came up with is that you can take any antenna and make an EH antenna out of it. And what you simply do, you tune the loop up on your frequency that you want to operate on. Then you build another network that's a 90-degree phase shift network to feed it with. Now it becomes an EH antenna because the electric magnetic field occurs simultaneously. But what it does to a small loop is kind of unique. We think about a small loop with the radiation coming off the sides of it, right? And a hole through the center. What happens is this reverses it. Now the radiation's out the center of it and nothing off the sides. So now what you do, envision just turn up on this way. Now you have an antenna that radiates that way. That's what you want on 80 meters, right? Real whiz-bang antenna. I had one on the back of my truck like that. Great antenna. Very narrow bandwidth, very high voltage on the capacitors, but works like gangbusters. And it turned out that on that one, what I did, I just sort of went around the perimeter of the back of the pickup truck and raised it up, about a little higher than just above the roof of the pickup truck. When I measured the antenna, when I first built it as a conventional antenna, conventional loop, I wrote down all the numbers. I don't remember exactly what they were. Then I went in and I made this conversion by putting this network on there and feeding it. And when I did that, the efficiency went from 14% to 84%. The bandwidth increased in that same proportion. So it's a heck of a good antenna. But for some physical reason, I finally took it off my truck. I was playing with some other stuff. So I don't really, I build a lot of antennas, but I don't use them very long. I put them up and figure out, well, it does this, does that, whatever it does. Then I got a better idea and I go on to another one, right? So I didn't have it on there for a long time, but it's a heck of an antenna. Now, it's not very good along the ground, remember. But it's a good high-angle radiator. But then if you're close in, you don't need much along the ground. Let the guys pick it up the other way. Because most of the guys on 80 meters, if they're fixed, they're going to be horizontally polarized anyway, right? So it works great. So that's one solution to your problem. Now, what you got to do, though, when you build that network, that your 9-degree phase shift network, very critical how you do that. Best thing to do, if you want to pursue that, send me an email, and I'll give you the details. I'll calculate the numbers for you and tell you what to put on there. But it works like gangbusters. All right, now, have I got everybody's questions answered?